There are several filter design functions built into MATLAB for creating IIR filters. These functions allow a programmer to put in common characteristics of a filter, and these functions will output the arrays for the feed-forward gains and the feedback gains. We're going to look at two of these filter design functions in particular. The first one is based on the Butterworth filter design approach. The function in MATLAB is called butter. This function takes in as input variables the desired filter order and normalized cutoff frequency. So in many ways, this function behaves a lot like what we've seen before with the FIR1 function. But in this case, it's going to design an IIR filter. The second function we're going to look at is based on the elliptic filter design approach. The function name in MATLAB is ellip. This case, the programmer can put in different kinds of characteristics. So for instance, the programmer could specify the allowable ripple in the pass band or the amount of attenuation desired in the stop band. The function then will create a filter with a very sharp slope in the transition region between the pass band and the stop band. So let's switch over to MATLAB and look at a couple of these filter design functions for creating IIR filters. Here I've started a script called IIR functions. We're going to go through two different cases. One is to look at the Butterworth filter, and the next one is to look at the elliptic filter. So there's two built-in functions for these things. The first one we'll explore is the butter. And this function takes in two different inputs, N, which is going to be the filter order, and Wn or omega n, which is the cutoff frequency. So we'll specify those two things ourselves, just as variables. So we have N. And to make it easier to begin with, let's start out with a relatively low number, 2. So this is the order of filter, which is going to be the, as we'll see, number of samples of delay, both for the feed forward and feedback paths. Then we'll have omega n. This is going to be the normalized cutoff frequency. So we'll have a minimum number of 0 and a maximum of 1, and 1 is our Nyquist frequency, so this is halfway in between. The result of this butter function is going to give us two things. It will give us the arrays that we need, B and A, for our feed forward and feedback paths. Now what I can do is use freq z and plot them. For now, I'm going to leave off the semicolon on the end of this function. We can look at down below in our command window what the result of this function is. So here we have a low-pass filter. It's going to have a cutoff frequency at -3 dB here at 0.5. It's going to decrease the amplitude of high frequencies. One of the very useful things about working with IIR filters is that we're able to decrease the amplitude by a fair amount by still using a relatively low order. So just a few samples of delay on feed forward and feedback, we can decrease this amplitude by 40 dB, 50, 60 dB or more. So just to illustrate that, let's step the order up to 4. So still not a whole lot, but we're down here in the range of -100 dB, -150 dB. So really attenuating those higher frequencies. And right, our filter complexity isn't anything near what we had to do before when we used FIR filters for this. So again, we can see the order controls these gains here. All right, so let's look at changing this to a different cutoff frequency. So here, it's going to decrease it down here at 0.25. So along with having the low-pass filter, there are other types that we would probably want to work with. So one would be to make this a high pass, and it's going to do the flip it around where we have 0.25 as our cutoff frequency, decrease them here. We can also put in, like we've done with the FIR1, we can put in 2 cutoff frequencies, 0.75 and we're not going to want to have high here. We just want to have this be the only input variables we need are N and omega N. And so this creates a band pass where it reduces the amplitude of the lows and the amplitude of the highs, decreases them by a lot. We can also make this a band stop. And just to double check, let's look at the documentation here for our Butterworth. If we put in stop, we can turn this into a band stop. So that's our last one. And we can see we decrease the amplitude here in the middle of the spectrum, allowing the lows and highs to pass through. Then, now that we have the arrays B and A, we could use the filter function, just like we were doing before, with working with these IIR filters in general. Now let's move on and talk about the elliptic filter, because this one's going to behave a little bit differently, and it'll allow us as programmers to put in some different types of parameters. So here we have 4 different input variables instead of 2. Some of these are the same. N here is the filter order like we were doing before. Then we have these 2 ones, capital R, lowercase p, capital R, lowercase s. This is going to be the ripple that we allow as a programmer in the pass band, and then the attenuation we desire in the stop band. And finally, we have the omega p, which is our cutoff frequency. So let's put in some of these things and experiment with them to get an idea about how they're going to work. This result of this function will also give us B and A. So the nice thing is all these functions that work with IIR filters are set up so that we will end up with a similar result, similar arrays to work with. So let's make this 4, and we'll make omega p, could really just be any normalized cutoff frequency we want to put in here. So I'll make it 0.5. So let's plot this one. We also need RP and RS. RP, let's start out with something like 6. So 6 dB of ripple. It's going to be a lot. We're going to exaggerate it, but that will prove the point. And then attenuation, believe it or not, we want to put in positive number like 20 dB of attenuation. All right, let's run this and look at the result. So there's a lot going on in this plot, but we have our cutoff frequency. That's the point to pay attention to over here first. At our cutoff frequency, we have a very sharp slope that goes between our pass band over here and then our stop band. First thing to notice is that our stop band never goes above 20 dB of attenuation. We are always able to achieve 20 dB or more in this stop band. If you look over here in our pass band, we've allowed MATLAB to create a filter for us that has 6 dB of ripple that happens. So it goes up to 0 dB and it goes down to minus 6 dB. And it can have ripples that occur in the pass band. But the main benefit of the elliptic filter is that by trading off the ripple and the stop band attenuation, we're able to achieve a really sharp slope that happens right around our cutoff frequency. If you remember before with the Butterworth filter, it has a slow cutoff frequency. This one, we have a very sharp transition that happens between our pass band and our stop band. MATLAB will try and make this as sharp as possible. So we can change some of these things around. Let's make this like 60 dB of attenuation and look at the result. So here, MATLAB is going to try and fit a filter so that we can get as close to 60 dB of attenuation as soon as possible. But in this case, our slope isn't as sharp. We still have the maximum amount of 6 dB ripple up here. It's not perfectly flat across our passband, but in some situations that is acceptable for us. So we would prefer to sacrifice a little bit of that ripple to have as sharp a slope possible. Again, if we change the order of this, we can achieve a sharper cutoff. So that's another degree of freedom we have to trade around with. We can have 6 dB of ripple, sharp attenuation, but notice now our stop band stays below minus 60 dB. So those are several of the different parameters that we can play around with to achieve different types of filters. So here is our elliptic low-pass filter, and then how we can plot the frequency response because it returns for us B and A. So those are the essential things about knowing how to work with the Butterworth filter and elliptic filter functions that are inside of MATLAB. Very, very handy for designing complex filters that we can use now for all kinds of audio signal processing.